We can also form cyclic acetals instead of forming regular acetals by doing an intramolecular reaction. So let's do the intramolecular version where we form a cyclic acetal product. So with this type of reaction, you are still starting with a carbonyl in there, okay? And instead of using 2 moles of alcohol here, so you're using 2 different moles of alcohols or 2 separate moles of alcohols, I'm going to combine the alcohol into one molecule there. So I'm going to end up using ethylene glycol. Notice here that my 2 alcohols, this is going to be my first alcohol, and this is going to be my second alcohol. The system is called ethylene glycol. Okay, mechanism is going to follow exactly or proceed exactly the same as above in there. The reaction is going to proceed by an acidic medium as usual. We stated that one of the acids can be sulfuric acid. In fact, you can use variety of acids in there. Let's go ahead and list them. You can use sulfuric acid, you can use phosphoric acid, and a very, very strong acid that you can use is the para-toluene sulfonic acid. Remember this acid from organic one. Drawing its structure in there, this is the para-toluene, the sulfonic acid. Here you go. This is NOH in there. This is, no, actually, okay. This is the TS group. So this over here is the tosyl group. Okay, and this is the TSOH in there. TS is tosyl, which is para-toluene sulfonyl group. And if you couple that with the OH, then it's going to be called para-toluene sulfonic acid. Normally, this is the best acid that is used in these types of reactions. So we use the TSOH in there. The TSOH will still release an H plus, so you can work with the H plus. With this reaction, what I am forming is an acetal, and the acetal is going to be a cyclic acetal there. So on the carbon of the carbonyl, here you go. You're going to form your acetal, and the acetal is going to be, you are losing the hydrogen here and the hydrogen in there, okay? Because you are making 2 ORs. Up there, you made 2 ORs. So each alcohol lost the hydrogen, and you group those into one carbon. This is exactly the same. So each alcohol is going to lose a hydrogen, and you're going to group those into one carbon. But now you are going to make a cyclic um, acetal. So here you go. These are the oxygens and the 2 carbons of the ethylene glycol. This is the first carbon. This is the second carbon. The oxygens in there, and then you have the hydrogen. Of course, in this reaction, you are going to end up losing water, so you're going to end up having water in there. Let's go ahead and draw the mechanism of the reaction. So for the mechanism of the reaction, you are responsible for, here you go. So you have your carbonyl, and we are reacting this. We're going with the same steps in there, and the formation of the hemiacetal is going to be our guide, okay? So the first step in the reaction is the protonation of the oxygen before the alcohol attacks. When you protonate the oxygen, you are going to end up getting a reactive partial positive carbon. So this one is going to be partial positive and is going to be very reactive now for the nucleophile to attack. So once you do this, then we're going to go ahead and start with the first OH. Choose whatever OH you want in there. So my first OH that I'm going to choose is going to be this one over here. So that alcohol is going to come, attack the carbon, and form a lone pair on the oxygen. And I'm going to end up, again, my hemiacetal is my guide. So I want to reach a point where I have my OH here, my OR on the same carbon. So right now I've introduced the oxygen. This is going to be my OR, but the OR is protonated. I don't care about what is on the OR in here. This is the rest of the molecule. This is the rest of the alcohol in there. But I want this to be neutral now. So I'm going to go ahead and use the OTS negative. This is the conjugate base in there because the pyritoluene sulfonic acid, it dissociates into an H plus and the OTS minus. So that is going to be the conjugate base in the solution. And that conjugate base can come and attack the hydrogen. So it's going to come attack the hydrogen, form a lone pair in there, and here you go. I got my hemiacetal. So every time you're doing these reactions, reach your hemiacetal, and this is how you know that your mechanism is right. I have two carbons in here, and the OH in there. So now I've introduced my first OR. So this is considered to be an OR, and I have my OH. So here I'm having my hemiacetal. Continue in there. So we're going to go ahead and continue with the same steps. We're going to do another H plus in there. We are going to protonate that oxygen and make it water so that it goes, it leaves. It's a good leaving group so that it leaves. So this is going to be my water in this case. Positive charge, and then I have my oxygen, my two R's in there, and then my OH. So now I formed my water, which is a very good leaving a group in there. I need to kick it out. So to kick it out as I did before, I'm just gonna go ahead and do resonance in there because my point here is that I need to make this carbon more partial positive so that this nucleophile can come and attack it. To make it more partial positive, I need to introduce a double bond in there with the oxygen being a plus charge. So now I'm going to end up forming a double bond in here. I'm going to kick out the water this way. And I am forming my, my double bond. This is going to be an O. It's going to be a plus a charge. And that oxygen is connected to two carbons. This is one, this is two, and then an OH. Okay, here you go. So you can write it like this. Now, what I created is a very reactive partial positive carbon. So now the lone pairs are going to come, attack this carbon, and form a lone pair on this oxygen. And I'll form my part product. It's not the product yet, though. So here you go. So I'm going to end up having a hydrogen here that I will need to get rid of, but I made a bond. You see, I made a bond in here. This is the positive charge with the lone pair. This guy has two lone pairs. It already had one lone pair, and you added a second one. So now any base in the solution, which is the OTS negative, is going to come and it's going to take that hydrogen and add a lone pair, and you're going to end up getting your cyclic acetal formation. Glycol, this is a cyclic acetal. Why do we care about cyclic acetals? Now, cyclic acetals are used as aldehydes and ketones of protecting groups. So cyclic acetals, they can be used as aldehyde, ketone, protecting groups. Okay, let's have an example. So let's say, for example, if we had this dicarbonyl compound, and I want to change this into this compound over here. Now I know that because I went from an ester into a tertiary alcohol, so this is an ester group. I went from an ester into a tertiary alcohol. This is my ester. And I went into a tertiary alcohol in this case. I added two phenyl, so this is definitely Grignard. But if I am doing a Grignard is very reactive to every single carbonyl. So let's say, for example, if I want to do phenyl, this is going to be phenyl, since I'm adding phenyl over here, two phenols. Let's say if I'm doing phenyl MGBr in presence of diethyl ether and H3O plus, then in this case, the phenyl is going to add it twice here. You're going to make your tertiary alcohol, and it's going to add over here, and you're going to make your tertiary alcohol as well. So your actual product for this reaction is not going to be this product at all. The actual product for the reaction is going to be, so that same thing with the phenyl, MGBr, and diethyl ether, H3O plus, you're going to end up adding the phenyl group to every single carbonyl. So you're going to end up having a tertiary alcohol on that ketone, and then you're going to end up having a tertiary alcohol excess. This is going to be a tertiary alcohol. It's going to add an excess for that carbonyl in there. So you're going to end up getting a completely different product than what you need. So this is why cyclic acetals are very important, because I can protect the group that I don't want it to react with the Grignard. And then at the end, I can get rid of that protecting group by simply adding water in presence of an acid. So in order to achieve this reaction in here, we are going to protect the ketone. So let's go ahead and protect the ketone. And to protect the ketone, we are going to use the ethylene glycol, because those acetal reactions, they do work only on aldehydes and ketone carbonyls. They do not work on the ester carbonyl. So pay attention to that. These are reactions that we are considering for only aldehydes and ketones. So we're going to protect the ketone. And to protect the ketone over here, so we're going to end up getting an O, here you go, in there. And then you will have your ester. Now I can go ahead and do my Grignard. Your tertiary alcohol. As I said, I don't have to mention that this Grignard is in excess. It's going to keep reacting. The OCH3 is going to leave. Please review the mechanism of this reaction until you get your tertiary alcohol. So here you go. That is going to be my protecting group. And then I'm going to end up having my OH here, phenyl, and another phenyl in there. So now I added my phenols on this carbon and it changed it into a tertiary alcohol. Now I can go ahead and do hydrolysis over here. And this is the good thing about these reactions. They can be reversible by simply adding some water in presence of an acid. What you're doing here is that you are breaking the bonds. This is going to be your alcohol part, okay? So you're going to add a hydrogen here and the hydrogen there, and you are going to regenerate back your dialcohol in this case, plus that carbon is going to return back to its carbonyl. So you're going to end up having a carbonyl in there. Here you go, and the rest of the molecules. So I can return back to the carbonyl of the ketone. In this way, what I did is I protected the carbonyl of the ketone from the reaction with the Grignard. I did the Grignard on the ester itself, and then I got rid of that protecting group by simply doing hydrolysis in acidic medium. So the reaction here It's called hydrolysis in acidic medium in there. Cyclic acetals. The mechanism of the hydrolysis of the cyclic esters to go back to the carbonyl and the diol is found in your notes. Let's consider another example. Okay, so let's say, for example, so here we're doing the mechanism. This is the hydrolysis of acetals in acidic medium. So the hydrolysis of acetal, this is the reverse of the acetal formation. You start with your acetal. This is an example in there. Okay, so this is an example. I just wanted to do another example than the one that is in the notes. What you want is, this is the final product. So you want to hydrolyze in presence of an H plus, and your final product needs to be, see that carbon that holds the acetal. You want to return it back to the carbonyl. So you go ahead and you return it back to the carbonyl, plus the OCH3 is in there. These are the ORs. You just add hydrogens to them, and those are going to become your alcohol. So now I know that my alcohol is going to be CH3OH, and this is going to be in excess. This is going to be the product of the hydrolysis, and it is again a reversible reaction. It's exactly as I did up there over there whenever I did the hydrolysis over here. So I broke these two bonds. I sticked a hydrogen to each of these oxygens, and then I made a carbonyl in there. Okay. So the mechanism of the reaction. Now, remember that what we're doing here, what we're doing is we want to kick out both of the OCH3s, both of them. Hydrolysis happens in presence of H plus, and since I'm doing hydrolysis, this means that my nucleophile is going to be water. So I am adding water in this case, because after all, see that oxygen formed from the carbonyl, this is going to come from the water. So my first step here, as usual, it's going to be the protonation of the oxygen. So step one, since my oxygen here is going to be a neutral nucleophile, then it's going to get protonated by the oxygen in there. I want the OCH3 to leave, and it cannot leave unless it is protonated. Okay, here you go. And then I'm going to have my OCH3 in there. So this is going to be my first step. I want to make it leave. So to make it leave, I can do a simple resonance in this case and form a double bond, and the CH3OH can leave, and I now managed to have, or to get rid of, my first alcohol in there. I introduced the carbonyl with an O and the CH3. Why? Because I need my nucleophile, which is water, to come and attack this carbon. So I want to make this carbon more reactive, as usual. Okay? Plus the CH3OH. Here you go. In there. So that is going to be a leaving group. It's not a nucleophile. Now, the nucleophile is going to be water. So water is going to be now my nucleophile, and water can attack. Remember, in these reactions, our intermediate is the hemiacetal. Whether you are doing acetal formation or whether you are doing hydrolysis of ester like I'm doing right now, your intermediate is the hemiacetal. So this is going to be my guide. So I want to form the hemiacetal in there before forming the carbonyl. So water is going to attack that partial positive carbon in there. Take out these lone pairs. They shouldn't be. It's supposed to be a plus charge in there. And I'm going to form a lone pair on the oxygen. And you're going to end up forming, this is going to be the O, CH3 over here. The oxygen It is not hemiacetal yet because I want to get rid of the extra hydrogen over here. Now we can use any base in the solution, like the HSO4 minus, in order to come and take that extra hydrogen over here and form a lone pair. The reason why I'm doing this because I want to form, I'm going backwards in the acetal mechanism because I am doing the hydrolysis of the acetal now. Since I'm going backwards in there, I would need also to form the hemiacetal. So this is going to be my OCH3 in here. So now what I did is I formed my hemiacetal. Okay. Now, after forming my hemiacetal in here, remember that I want to get rid of the OCH3. So to get rid of the OCH3 in there, we're going to go ahead and do the acid again, because the OCH3 cannot leave with a lone pair on the oxygen. I need to protonate the oxygen to make it leave. And to protonate the oxygen and make it leave, I would need to use an acid. So I'm going to use the acid again, which is the H plus in there. And the acid is going to protonate the OCH3. I want to get rid of the OCH3. To get rid of the OCH3, it needs to be an O positive to leave. This is the rule in there. So you have your hydrogen, lone pair positive over there, and then a CH3. Now, to kick out the OCH3, we're going to do a simple resonance. So the lone pairs are going to close over here, and we're going to kick out our OCH3, and we're going to form our double bond OH plus the O hydrogen and the CH3. This is our second mole of the alcohol over here. So we kicked out our first mole of the alcohol, and now we're kicking out our second mole of the alcohol. We're returning back to the carbonyl, so all what we need to do is use the base again, any base in the solution, and that's going to come take that acidic hydrogen, and you're going to end up getting your carbonyl.